Okay, today we're going to be thinking about friction. So let's begin by thinking what friction is. So it's useful if you have a Newton balance to play around with it and just see what happens. So let's think about a horizontal surface and we've got a block of wood. And let's think we've got attached to this horizontal, this piece of wood, Newton balance. Now Newton balance is just something which is used to measure forces. Now, if our block of wood is not moving, we have the weight down here, mg, and we have the normal contact force acting on it. And there's no other forces. This block of wood is in equilibrium, it's not moving. And in this case, it experiences no friction. Let's say we apply a small force. Let's say the force is equal to 2 newtons, but the block of wood is stationary. This tells us it's still in equilibrium. So there must be another force acting in this direction which is equal to our 2 newtons, and this force is friction, and it must be equal to 2 newtons. Otherwise the block of wood would move. And you can see this can be the case that if you imagine having something big and heavy and you apply a force to try and move it and it just doesn't move. And if you were to get a book on it, put it on the table and try it and just apply a little bit of pressure to move it, it doesn't always move. Now we're going to increase our force. Let's increase our force by, so we've got our mg, our mass hasn't changed, we've still got our contact force, we've got our Newton balance, and this time we're going to give the force equal to 3 newtons, and it still doesn't move. So we've got our friction, the friction is now in the opposite direction of 3 newtons. So what we see is the force of friction increases. Now imagine a situation when we're increasing the amount of force on our block of wood and we get to this point where it's just about to move. If we apply any more force, that block of wood will move. We say that we're now in limiting equilibrium. So limiting equilibrium is the point when the object is still in equilibrium but applying any more force will cause motion. And at this point, friction is at its maximum value. Now, let's think about where friction acts. Friction is between the two surfaces, okay? So the two surfaces that are in contact experience friction. Where there's friction, the surface is said to be rough. If there's no friction, the surface is smooth. Now, each pair of surfaces has a coefficient of friction. And we call that mu. It's the symbol mu. And it is a numerical value which limits the amount of friction a surface experiences. Now, typically, mu is between 0.3 and 0.7. You can get mu reaching 1. If that was the case, the coefficient of friction is extremely large. For a smooth surface, the coefficient of friction is going to be close to 0. Now, the limiting value of friction, that maximum value that it takes, F is going to be equal to, mu R. So mu times the contact force. Below the limiting value, F will be less than or just coming up to equal to that limiting value. What does friction depend on? It depends on the size of the normal contact force, and it depends on the coefficient of friction. Now, you may think that the friction will depend on the surface area that's in the size of the surface area in contact with each other. For example, if you might think if you had a very large piece of wood, that would have experienced greater friction than, say, a book of the same weight. However, that's not the case. The surface area in contact with the surface plays a negligible role in the size of friction. if you think about if you've got a larger surface area in contact with a surface, the weight is going to be more evenly distributed, so that although there's a greater the surface in contact is bigger, the normal contact force would be less. Now, because friction depends on the normal contact force, we say that friction is part of the contact force. Now, the normal contact force R, let's just think of our book on top of here, that is R, and this is mg. So our contact force R is perpendicular to the surface, and F, friction, is parallel. So we can find the total contact force by using Pythagoras. So the total contact force, C, is going to be equal to the square root of R squared plus F squared. So we consider this is going to be R, this is F, friction, and this will be the contact force. Consider the vectors, and this will be some angle theta. So the direction of the total contact force is an angle, which I've got here is theta, which is equal to tan, the inverse tan of the force over friction over the contact force. When an object is stationary and about to move, the friction is at that limiting value. We say it's in a limiting equilibrium. We can say at the limiting value, i.e. limiting equilibrium, we can use the phrase on the point of slipping. This means that any extra force will make the object start to move. Now sometimes it's not clear which way friction acts, and I'm going to explain why this is the case. So suppose we have a car on a rough surface and we have a tow rope attached. So we're going to just, here's our rough surface, and it's on a slope, and this is our car, and there's a tow rope attached, and I'm going to call this the force on the tow rope T. Now imagine just imagine anything on a surface. Imagine having a surface and putting an object on it. If this object doesn't move down the slope, friction must be acting in the opposite direction. Otherwise, it would just slide right down. If you put something on a really smooth surface, it'll slide right down. So friction can be acting up the slope. So we've got our car here and we've got a tow rope on it, applying a force, which we're calling T. And the tension in the rope is acting parallel to the line of the slope upwards. Now we don't know if the tension is there to try and pull the car up the slope. So you might be trying to get this car to move up the slope, and so the tension in the rope might be trying to pull the car to get it to move up the slope. Or this rope might have been attached to the car, because if the rope wasn't on the car would slip down the slope. So maybe this rope here is just attached, and it's not being applied. The tension isn't being applied to pull the car up the slope. Perhaps it's just there to give enough tension to stop the car rolling down. So we've got these two different scenarios. So in the first scenario, if this rope is applying enough tension just to stop our car rolling down, we will have friction also acting up the slope. And we have our mass, the weight of the car, and we have our contact force, and we have theta. Now, in the scenario where our car is still sitting on our slope, it's still got mg coming down here, the weight of the car, it's still got our normal contact force, and we've still got our rope with some tension. But this time we're trying to pull the car up the slope. We're wanting to get that car up the slope, and it's not budging. It's still in equilibrium, but we're really pulling, and the car's not moving. We've now got friction acting down the slope. When it's not clear what direction friction's acting on, we must make an assumption about what's happening in the subsequent motion. And we need to be aware of the significance of getting a negative value. So if we assume that friction acts in one direction when solving the equation, if friction has a negative value, we've made a wrong assumption with regards the direction of motion. Friction will have the same magnitude but in the opposite direction. So you should be stating the direction of motion, the direction of which friction is acting when you do your diagram. The value of friction given by the equation may be too large because friction is limited by mu times r. If this happens, then the object cannot be in equilibrium. If the value calculated for friction to keep the object in equilibrium is larger than the limiting value, an object cannot remain in equilibrium. So let's look at some questions. So let's imagine we've got a box of mass 5 kilograms, and it rests on the horizontal. The box is pulled by a horizontal force of 8 newtons, find the total contact force. Now, some things to note: it's at rest, so the forces are in equilibrium, and it's on the horizontal. So here's our horizontal, and here's our box. We have 5g in this direction. We have our contact force R. We're told there's an 8 Newton force in this direction, and therefore friction must be in the opposite direction. So, first we want to find the vertical. So we're going to resolve in the vertical and the perpendicular components. So the vertical component is R and 5g. So R must equal 5g, which is 50 newtons. Now we're going to do the horizontal component. So 8 newtons must be the same as the friction. So now we're just going to use Pythagoras. So the total contact force must be r squared plus f squared plus r squared, all square rooted, and that therefore will give us 50.6 newtons. Let's look at another example. So now we've got a box of mass 8 kilograms on a rough slope at an angle of 20 degrees to the horizontal. The box is held in limiting equilibrium by a force of 10 newtons. And that's parallel to the slope. And we want to find the coefficient of friction and the magnitude of the force. And so that's A and B. We want to find the largest force up the slope, where the box remains at rest. So the first scenario, we've got our box, and we've got 8g down here, we've got 20 degrees, we've got our normal contact force, and we have 10 newtons. But in this scenario, it's in a limiting case. It's just that 10 newtons in this scenario is just stopping our box from falling down the slope. So we've got some frictional force in this direction. So we want to resolve the perpendicular. to the slope. So that would be our, think about, we've got, that's R is perpendicular to the slope. And we have our MG here. So R would be equal to 8G cosine of 20, which is 75.2 newtons. Now we want parallel. I'll do it here actually. Resolve parallel. To the slope. So we'd have RG sine theta is going to be equal to, well, it's going to be equal to 10 plus F. So that's going to give us F is equal to RG, 8G sine theta. F is equal to 17.4 newtons. Now, we notice it at limiting equilibrium, so F must be equal to mu R. So mu must be equal to F over R, which is 17.4 over 75.2, which is 0.231. And that won't have any units because it's a force over a force. It's a coefficient, so it's got no units. And then we can use Pythagoras. I'll do Pythagoras over here. To get the total contact force is going to be F squared plus R squared. Slotting your numbers in, that's going to be 77.2 newtons. Now, for the B, for the largest coefficient, for the largest, well, we'll draw it first, 20 degrees. Here's our box. We've still got 8G, we've got our contact force R, and we have some force F up here. Now this time we want to know what is the large, if we were to keep applying force, what would be the largest force that we'd be pulling up on this box before it started to move. So this time friction is going to be pulling in the opposite direction. So we're going to resolve the parallel forces. So this time 8G sine theta plus F must be equal to, we'll call this force P, so we don't get confused. P. Now we have R from before, so we know R was equal to 75.2 newtons because that's not going to change. And we know that F from before was mu R, which was 17.4 newtons. That, although F is now in the opposite direction, because the contact force is not changed, mu won't change because mu is the coefficient of friction. It's to do with the surfaces. Friction, although it's now in the opposite direction, is still the same magnitude. So we can use that to now work out that P would be 44.7 newtons. Now let's do another one. A waste container, otherwise known as a bin, has a mass of 400 kilograms and is in equilibrium on a rough slope at an angle of 18 degrees to the horizontal. The coefficient of friction between the slope and the skip, well, it's a skip, not the bin, is 0.3, and it is held in equilibrium with tension T. Find the range of values for T. So let's look at the first one. What's the minimum? So that will be 18 degrees. We've got our skip. We've got 400 G. We've got our normal contact force R. We've got T. And we've got our friction here. So again, we're going to resolve the perpendicular first. So that would give us R is going to be equal to 400 G cosine theta, which is going to give us 3,800 newtons. And now we're going to do the parallel. This time 400 G sine theta will be equal to T plus F, because that component is going to be down the slope. So that will give us now we can work out F because we've been told the coefficient of friction is 0.3, so it's mu, and we've just worked out R, so that will be 0.3 times 3,800, and so F is going to be 1,140 newtons. So slotting that in, working it all out, we'll get T is 94.8 newtons. So that's the minimum value. What's the maximum value of T? So this is the case when we've got our skip, we've got our 400 G, we've got our normal contact force. This time, this is when friction will be coming down the slope, and the tension in the rope is such that it's trying to pull that skip up the slope, and it's just not quite got enough because of the frictional force acting down the slope. So again, R is going to be the same as this. R is still 3,800 newtons, but this time for the parallel component we're going to have 400g sine theta plus F equal T. Now F is going to be the same because R is not changed, the coefficient hasn't changed, so that will give us, so that will mean T is going to be equal to 2,380 newtons. So the range will be 94.8 is newtons is less than or equal to T is less than or equal to 2,380 newtons. So I hope that helps.